from the normalization group equations for these. And you find that, first of all, for large lambda of nu, and I'll try to quantify that, what that means, but if MH is fairly large, like a few hundred GeV, for example, then the lambda squared dominates. And if you do the plot, if you just calculate what happens to lambda, what you'll find is that lambda starts out at some value that is, here's nu, so here's some lambda of nu here, it increases, and at some point it just goes off to infinity. It becomes nonlinear and it shoots off exponentially to infinity. And this is called a Landau pole. It's very frequent if your theories of gauge any coupling constant can go to infinity. Now, of course, and that was very similar to what happened in QCD when you come down in energy. I said at some scale it just shoots off to infinity. That was basically a Landau pole also. Now, when you hit a Landau pole, obviously the theory doesn't make sense anymore. The approximation breaks down. To calculate where that happens, you're working to some finite order perturbation theory for the way, so obviously that approximation breaks down. But it's unlikely, as a proof, it's unlikely that will really come in stable. So if this happens, you're in trouble. The theory doesn't make sense. But you can sort of evade that if you say, require sensible theory up to some scale lambda, capital lambda. In other words, if the standard model is only an approximation up to some scale lambda might be 1 TeV, it might be 10 to the 5 Joule, it might be the Planck scale where gravity comes in. At some point the theory is going to break down, and you don't care if there's a Landau pole at a larger scale because the theory is not meant to be valid there. However, if you want the theory to be valid up to some scale higher than where the singularity, then there's just not consistency. It doesn't make any sense. So this gives a theoretical upper bound on the possible Higgs mass as a function of this lambda. If you take lambda to be 10 to the 18 GeV, it's basically the Planck scale. If you say the standard model has to work up to where gravity comes in, that puts an upper limit of, let me try to draw this somewhat precisely, 200, 600, 400. Basically, there is a theoretical upper bound like this. If you say that the standard model is to be good only up to, say, a TeV, then it means MH is less than about 500. Or if you insist on it being good up to the gravity scale, it means the MH is less than about 180. So that's a fairly reliable theoretical upper bound. It's also supported by other related but not identical calculations. I mean, this is totally independent of the so-called Higgs hierarchy problem that I'm not going into right now. I'll talk about that on Friday. This is a different thing. So there is an upper bound. On the other hand, and it's really about 600 for any sensible lambda, there is a theoretical lower bound as well. That is, the second diagram dominates for low M Higgs. And that second diagram, if lambda starts out small, it will eventually get smaller. And if it goes negative, then you don't have a stable vacuum. So the vacuum becomes unstable and it exists too low. Again, if you say that the theory really only makes sense up to some lambda, then all you can say is you don't want that to happen below lambda. Well, this vacuum stability puts a lower limit that looks like this. And basically, the observed Higgs mass is here. Well, let me just say one more thing in words. This is the standard model. I said that in the supersymmetric extension, there was a theoretical upper bound because lambda is not a free parameter in supersymmetry. And basically, that theoretical upper bound in supersymmetry was pretty much overlaps the theoretical lower bound in the standard model. So for many years, people said, well, if we observe a Higgs, and the vacuum stability doesn't apply in supersymmetry because that means the nu scale is already there at low energies. So for many years, people said, well, if you find a Higgs up here, it's consistent with standard model, but not supersymmetry. Whereas if you find it very low, it's consistent with supersymmetry, but not the standard model. Well, of course, what happened was it's now observed, and I'll spend a little bit of time tomorrow on how it was produced and observed and the decays and all of that. But it's basically right here. It overlaps this region at about lambda 10 to the 11 Joule. It is uncomfortably low for the standard model because it says that the vacuum actually, it says that our vacuum is unstable but metastable. If you're left alone, it would be unstable. So if the P versus the side, this is what you would have without those higher order corrections, and what you would get without the corrections, and for I'm sorry, let me try to draw this a little better. You can raise that somewhere. So I'm trying to draw the potential, including these effects, and basically on this axis, I'm just drawing the relevant scale, which will tell me where the minimum really is. So this is lowest order, but including those corrections, an unstable vacuum would look like and a metastable vacuum looks like this. Or I'm still not drawing it well. The metastable looks like this. That's metastable. What that means is if this is our 246 GeV and the potential looks like this, then eventually the vacuum will decay and the whole universe will go up all of it. Now that's actually okay as long as the expected lifetime is more than 10 to the 14 years, or 14 billion years rather, longer than the observed age of the universe. Don't sound a military law, but they might get some ideas. But anyway, but people are not necessarily comfortable. Anyway, the observed case, if you have standard model, is such that this is about 10 to the 11 here, and so the vacuum, if there's really no new physics up to that scale, then our vacuum would be as we have observed now is metastable. However, there could still be supersymmetry or something else in this case that is cut off the calculation for that top diagram, and it becomes irrelevant. However, I think supersymmetry is somewhat difficult to get. I think it's 125. Okay, are there any quick questions? How is it the modern standard model, but namely neutrino physics and neutrino maths, which has been a major development in the last 20 years? Are there any questions? Well, I want to finish up talking about the Higgs today and then go on and talk a little about neutrino physics. And yesterday I presented some of the constraints. Within the standard model, there are a series of constraints based on the running of the quartic coupling. And if the quartic coupling, of course, is related to the Higgs mass at no scale by mh equals 2 lambda evaluated at the weak scale times u itself. But at higher scales, the lambda for sufficiently large initial value, it increases because of the lambda, the higher order terms than lambda in normalization group equations. Or for small lambda, it's actually top quark roots dominate and drive lambda to zero at a negative at large scales, which would destabilize the vacuum. And this would make things non-perturbative. So there is some sort of range that is possible theoretically between, or perhaps 40 and 700 or 800 GeV if the new physics comes in at a very low scale, and that can be fairly rigorous on other related grounds. And if there's no new physics up to the Planck scale, then there's only a fairly narrow range between about 100 and 180 that is allowed. Now, and of course, it's going to turn out that the experimental value is such that the experimental value is out there, so that the vacuum is destabilized at about 10 to the 11 GeV. However, it's metastable and lives longer than 14 billion years, so it's technically okay. There were direct searches for the Higgs, and the most stringent ones prior to the discovery were from the E plus E minus collider at CERN in Geneva, Switzerland, and above the ZPO, that's just virtual Z goes to Z plus Higgs, that's got a lower limit. There are indirect limits from the role of the Higgs in ranges of corrections for precision electroweak physics, which narrowed it down to being less than about 150. And if one extends to supersymmetry, then there are theoretical constraints. Lambda is no longer a parameter, it turns out that supersymmetry is related to Higgs couplings. And that puts theoretical upper limits at about 130 in the minimal supersymmetric version and 150 in extended versions. So all of this is sort of pointing to a light pitch between 114 and 150, and if discovered in that range, it would be consistent with, but would certainly not prove supersymmetry. Okay, now to actually search for the higgs, one has to talk about how does it decay. And, well, that depends on the mass. And if the mass is less than twice the W mass, the decay is dominantly into dV bar. Remember the couplers, I'm not going to write them all again, but the interaction strength for a fermion is proportional to m fermion over u, and for W or C is proportional to m, say, W squared over u, or if it's a Z, it's C squared over u. And those are the basic vertices that are relevant to us in the existing Higgs searches. Okay, so if this is less than 2 MW, that means it cannot decay into a real W plus W minus pair, it's not photomatically evolved. And so it will decay predominantly into the lightest fermion that is possible, and that would be dV bar. I'm already assuming that we're not down at, 1 GeV or something. That's long since been excluded. However, and the weight for this is easily calculable. For any fermion, the weight is the number of colors, so this is 3 for a quark or 1 for a lepton, and it turns out to be conveniently written as 4 root 2 pi beta f cubed mh. Beta is just the velocity of the fermion from the decay and the Higgs rest frame. The main point is that, however, that this is almost impossible to observe directly at the Hadron Collider, because there are so many QCD ways to make dV bar pairs that when it's swept by Dirac. I'll mention ways around that, but it's very, very difficult. So hard to observe. There are also, the next most important is a 2 pair of tau leptons. This also has good backgrounds, but they're not directly QCD, but you can make tau plus tau minus by photons or other means. So this is the next most important. So that would be lighter than 2 in W. I will just mention, although it's no longer so relevant, for H bigger than 2 in W, then the dominant decay indeed is in W plus W minus or in the ZZ. Let's say greater than 2 in G. Then, because here, you have this is a negative gauge coupling, and W is G times E, so it's a gauge interaction strength, which is not huge, but it's not tiny like some of the fermion couplings. So this would be the dominant thing above about 150 or so. And if it were extremely heavy, twice the top quark mass, it would decay into dV bar. Okay, so the first new generation searches were done at the Tevatron, that's the Antiproton Collider in Fermilab, and they were really only sensitive to this type of decay. And they just did not have enough energy or enough events to be able to be sensitive to other things. So basically, they were only sensitive in a narrow range of masses around 150 GeV, and they didn't see any events. And they got down to the level of sensitivity that would be expected for the. Maybe I should make. Here's the mass of the Higgs, and so basically, this was excluded by Lep2. This was suggested to be in this range by theory, but from precision experiments, but experimenters never pay any attention to what the theory says. So the Tevatron search basically excluded this region. And there were, and there were good theoretical reasons that it could in principle have been much heavier. Okay, but then at the LHC at CERN, this is a PT machine, and they were at much